Hi, Slava.
Okay, very good. So let's get started with Zheshwan telling us about functional Bootstrap.
Hi. Thanks. First, let me thank the organizers to give me the opportunity to present our study on the Bootstrap, numerical Bootstrap using the analytic functionals. So in the beginning, let me summarize the main point of this, the main result of this study. So this study, unlike the previous studies using the analytic functionals, it is in 2D and 3D. And we use the auto approximation to do the numerical implementation, and all the numerics in this study, they are done by machine precision, double precision. And from the result of our study, it seems analytic functional as a basis in the higher D numerical conformal bootstrap, it has a better convergence. And at last, we discovered because this has better performance, so we can reach much farther than the previous result. I mean, in the single correlator bootstrap. So we discovered some new kinks in the gap maximization. Yeah. So this is the main result. Let's start with a very schematic and a very brief review of our state-of-art implementation of the conformal bootstrap. So we have the crossing equation. And plus some additional constraint. Usually this constraint could be some symmetry group or some additional assumptions of our spectrums of the theory. So the first thing is that we will use derivative basis at z equals z bar equals 1/2. So crossing symmetric point to make this, to extract or project this crossing equation onto the basis of the derivative. And then the second is that we use a rational expansion to compute these derivatives. And by this, thanks to this rational expansion, we can approximate all these derivatives in terms of the polynomials of the delta. So that at the last step, we use SDPB, which is an efficient arbitrary precision solver to solve this SDP and use a navigator to decide where the allowed region, where we can find the allowed region of our spectrum under this constraint. Okay, among these elements, the first one, the derivative, is the most stable one. By the stable, I mean since the first work of 2017 of modern numerical bootstrap, and till now, the derivative is in a dominant position. So to consider other possible ways to or other possible basis of functionals to project these crossing equations on. Usually, we want it to satisfy several conditions. Here, I list 5. I think it's the most important conditions that a good basis. We believe a good basis should satisfy in order to do some numerics. Sorry, I'm writing it a bit small, but it's okay. I will erase it later. So for some other purpose. So the first one is instant. So it must be finite. This is instant. We don't want to, in the numerics, we don't want to deal with some infinite things. So this is instant. The second one is also almost instant. That is, we want the functional action to pass over the infinite sum over the OPE expansion. The completeness is a deeper constraint. That is, if this we want this basis of functional, it captures all the information in the crossing equation. This is in the mathematically, this is how it is written down. Oh, okay, I forgot to mention that this indices of the functional, it must be a integer. Otherwise, or at least it is countable. Otherwise, you don't want to list it as some real numbers or something like that. The other reason that is just for Bootstrap, we want the positivity condition, or more precisely, I want to call it the asymptotic sign definite. It must be positive. It can also be negative, but it needs to be asymptotically positive sign definite, so that we can do some finite linear combinations of the functionals to make some functional that is positive everywhere except some finite region, so that we know that in this region there must be something. So this is a positivity condition. The last one is a practical demand. That is, we don't want anything that is perfect, except it is useless. So that we must have some mature way to cook up some efficient ways to evaluate this functional evaluation. So these are the 5 conditions of it. Let's look at for warm up. Let's look at how the derivative basis is satisfy all these 5 conditions. So we can write a derivative basis. Finiteness, this is instant because it is analytic at the crossing symmetric point. For the swapping condition and the completeness, it comes from the absolute convergence of the OPE expansion, so that this guarantees that the crossing equation, it is analytic in the neighborhood of the crossing symmetric point. So the swapping condition and the completeness is almost instant from this convergence. The positivity condition is actually less instant. It comes from our well-known formula for the rational expansion of these derivatives. So that in the asymptotics, the rational expansion tells us that our asymptotic is dominated by some known functional, so that the positivity is guaranteed. And from the same formula, I mean the rational expansion, we can compute it efficiently through a series of work. So this is how the derivative functional, it satisfies all these conditions. Generally, it is not so easy, I would say, to cook up some functionals that satisfy all these conditions at the same time. So this dominance of the derivative have never been seriously challenged until 2016. That in that year, Dalimio came up with a functional that gives the extremal functional of the 1D gap maximization. So it is, let me, where I write it. And this functional, 2 years later, it has been generalized to a complete basis of the crossing equation of 1D CFT. That is There are 2 papers by Dalimio and Miguel. I will not assume that everyone is familiar with this story, so I will give a very brief introduction of these spaces. These are called I would call it the alpha and the beta functional. There are two categories of such functionals. One is called the fermionic, the other is called the bosonic. Let's pick the fermionic just as an example. So that these functionals, they are due to the generalized free fermion, which is free fermion theory in the ADS2. So the delta NF, it is equal to 2 delta phi plus 2n plus 1. So for the fermionic basis, it is due to the generalized free fermion in the sense that alpha m delta n equals delta nm. Beta m delta n equals 0. In this sense. So this is one of its property. The other property is that we can expand in 1D there is no spin. Expand any crossing vector in terms of the okay. Of the crossing vector at the GFF point. For explicit construction of the functional, I would write it as a double integral. This is the explicit implementation of the functionals. Here, W can be alpha and beta. But there is a much better formula to write it down, that is in terms of sine square, which makes the structure of the functional more explicit.
Maybe you want to change pen.
Okay. Oh, this is not a good pen. So the previous pen is not a well-defined pen in this sense. Okay, this is much better. Yeah, this seems this takes some time, but we will need these formulas later. G of n, here the kernel, the previous kernel is h of n, and this is g of n. It is some discontinuity of h. Yes. So by this transformation, we remove the discontinuity from the f to the h, so that what is the functional looks like? Well, the functional, it will look like, let me just draw the beta 0 of delta and the delta. Here is 2 delta phi plus 1. So it will look something like that. Schematically. So it is basically sine square. And here, this factor, it will have some poles to cancel the double poles here, double zeros here, to make it a single zero. And one of the instant consequences of this functional is that it is an extremal functional for the gap maximization, which means that we must have something here below the 2 delta phi plus 1. And we know that this gap is saturated by the GFF, generalized free theory. So that this is why this is an instant result of these functionals. Yes, so let's look at how this functional alpha and beta, how they satisfy these 5 conditions. Of course, sorry?
The function Gn of z that you didn't give, I'm not sure.
Gn of z, it is by h.
H or G, the
Yeah,
one.
h. There are sometimes they are rational functions, and sometimes there are some functions of the log of that. So their explicit construction is, well, for integer or half integer of delta phi, you have a nice formula in terms of the Legendre polynomial. But for general delta phi, they are very complicated. So I will talk about it later. A better way, I mean, this is through the integration by some kernel. But for higher dimension, this this multivariant integration, you cannot calculate it very easily or precisely. So we don't use this formula to calculate it. I will talk about it here. So let's just discuss about this computability. That is how to calculate it. Actually, these functionals, they are related by some of the Witten diagram construction. That is, some of the crossing symmetric Witten diagrams, you expand it in terms of the conformal block. And the coefficient, they are the analytic functionals. This is how we calculate it. Well, then through this way, it is actually some 7f6, or the derivative of 7f6. And this calculation, we can do it very efficiently in Mathematica up to any precision. So this is how the computability is solved here. But this is not solved by the original paper of Dalimio and Miguel. For the first 3 conditions, this is actually proved in that paper, mathematically rigorously. And for the positivity, it's a bit more subtle, so that for integer or half integer delta phi, we have the exact result of it. But for general delta phi, we know that it is some 7f6. But no one really bothered to prove that this function has some positivity, nice positivities. But we draw it, for every delta phi, we draw it. So this is strongly believed that this is true. No one really doubted it satisfies this positivity condition. And in another work, the numerical bootstrap in 1D using these functionals is already explored. So this is how the 1D function. This is the story of 1D functional. Let me give some final remark. The first remark is that there is not only the bosonic and we discussed about the fermionic. There is also the bosonic. And the second one is, we talked about this is the so-called crossing vector, which is a difference of the conformal block. There is also the anti-crossing vector, which is sum of the conformal block. They are also interesting. Sorry. And for this anti-crossing vector, we also have a complete basis of these functionals. We call it plus type functional, and this one we call it minus type functional. Why these are interesting? Because, well, when we are considering the mixed correlator situation or the crossing equation with global symmetries, it appears. So we will see that alpha, schematically, alpha m h delta n is equal to delta mn, ... Yeah, there we have another family of such functionals. So this is the story of 1D functional. And there, for the higher D, the most well-known basis, I would say it is the nu ig and mu ig. From the seminal work of dispersive sum rules. In that work, there is a basis, a direct generalization of the 1D functional that's also due to the generalized free theory in the sense that the element of the functional and the element or the operators of the GFF, they are one-to-one correspondent. There is a functional called alpha NL and beta NL. One of the disadvantages of this basis it is that it doesn't satisfy the swapping condition over there, but we can do some subtraction. That's why the mu and nu comes from. We do some finite linear combinations of these alpha and betas, and we reach a functional that is swapping with sum over the OPE. So the finiteness swapping is satisfied. The completeness from my discussion with Dalimio, it seems that there is no rigorous proof of the completeness, but it seems most of the people, they believe that it is complete. For the positivity condition, this is a bad news. So that through some numerical exploration, it seems we can never cook up some linear combinations of such functionals, mu and nu, such that it satisfies the asymptotic positivity we mentioned before, which means that if we use these functionals to do the numerical bootstrap, we can never get it's very hard to get a valid bound. But this doesn't exclude the infinite linear combinations of mu and mu. We will come back to it later. By some infinite combination, we can cook up such thing. But numerically, we cannot cook up infinity. Computability, this is a question mark. We don't know how to, we can, to the best of my knowledge, the best way to compute it is through some direct integration, which is not efficient enough. Okay, considering this point, actually there is another set of functional that is believed to satisfy all these 5 conditions in the higher dimension. That is called the product functional. Let me write down its definition. Yes. Yeah, this is a product functional. Compared to the previous functional due to the GFF, this functional, it seems very naive. So the most straightforward but not precise ways to understand this functional is that it just acts the 1D functional we just defined, both on the Z and the Z bar section, just like the derivative. We act the derivative on the Z and Z bar independently. But you see, there is some tricky part. That is, it's not just a product, but through some mechanism, you cancel the anti-symmetric part of the 1 minus Z bar.
So, sorry, what is this argument of this last F? R Z bar or what?
R of Z bar?
1 minus Z bar.
Oh, sorry. Yeah. Let me make it clear. Yeah, there is a delta L. So to give us a better intuition of how this product functional looks like, let's study the 2D action. So the 2D conformal block, we know it in a closed form. I guess everyone knows it here. So it is g of tau z, g of rho z bar, plus g of 1/2 of here g is the 1D functional, so that we can cook up the crossing vectors in 2D. Let me write it a bit faster. So because the formula is a bit long. From this equation to this equation, this is just some very simple mathematical transformation, nothing deep. Yes, then you can act directly this action. Suppose there are some W1 and W2. We just define here the minus type and the plus type function. What will you get? Well, you will get W1 minus times W2 plus. Yes, this is a direct evaluation. This is very straightforward to check. For the higher dimension, this is acting on the two-dimensional crossing vector. For the higher dimension, we notice that there is crucial rules by Matthew. That the conformal block, we can decompose it with some lower dimensional conformal block. So we can define the crossing vector.
One short comment. Can you explain what this rho and tau are? I have a
Rho,
guess.
sorry, yeah. This is a mistake. Rho is delta plus L, and tau is delta minus L. Tau is a twist. Rho is delta plus L. Sorry for this omission. Okay, so this is a higher D, the D larger than 2. By this way, in principle, we can expand all the higher dimensional conformal block in terms of the two-dimensional conformal block. And just by some algebraic manipulation, we can expand the higher D crossing vector in terms of lower D. Sorry, there is something missing. There is a factor that is dependent on the delta phi and L. What is important is that these factors are positive. So if you, what we want to do? We want to do that. We want to expand all the crossing vector in the higher D in terms of the 2D and acting the functional, understand this functional action through the 2D version. One instant problem of it is that we are not very sure whether this functional action can pass through these infinite sums. Luckily, this is guaranteed that if you really check this action, this is an absolute convergence action. So this is guaranteed. We can pass through it. Well, how does it converge? Let me give some remark. So if you see let's see, we pick n, the nth term, a and g, and suppose this is our product functionals, and here it's f of delta plus 2n and j. It goes like 1 over n to the 6 plus 4 delta phi. Yes, this is a convergence behavior, so it is absolute convergence. And let's pick for the 3D. So for the 3D, delta phi must be larger than 1/2. So this is, I would like to say this is a strong power law convergence. And the second, here we define the product functional. There are, from our construction in 1D, there are actually 4 family of functionals. And from our numerical exploration, these 4 family of product functionals, they are by themselves, it seems they are all complete. That is, there is fermion, minus part fermion, plus type fermion, and bosonic, and also the fermion, bosonic, all bosonic fermion. Yeah, by themselves, they are independent family. Of course, you can mix them, but I want to say by themselves, it seems they are complete. And what's interesting about these different families of functional is their asymptotic zeros. A single 1D functional, they are like sine square. So the product functional through this formula, there are some quadratic of sine squares. So here, fermion, actually they are asymptotic zeros. They are not of GFF type, but some 2D critical Ising type. That is 2 delta phi plus 4n plus L plus 2. And this is in the step of 4. So you may find some zeros missing, but actually it is not missing because they are 4th order zero. And also for the bosonic, they are the 2 delta phi plus 2n plus L. Sorry, 4n, and also the 1st order. More interesting is the mixed type, that is bosonic fermionic. It has a GFF type asymptotic pole. Yeah, this is a GFF type. Okay. The third one is we want to comment on the relationship between these families of product functional with mu and mu here, which is also believed to be complete. Because of this factorized form, you can see that there is no one-to-one correspondence between the zeros of the product functional and the operators in the GFF. Actually, one of the functional, it talks to infinite number of the GFF operators in the product functional. So it is clear that if you really do a serious expansion, the product functional, they should be infinite linear combinations of the mu and mu families. Yes. Okay, at last, let's discuss how they satisfy all these conditions. So for the finiteness, of course. For the swapping condition, in Miguel's paper, it is shown that as long as your 1D functional is satisfied the swapping condition, the higher D satisfy. So this is guaranteed. For the completeness, not proof yet. We are just try to be confident about the completeness using our numerical exploration. And the positivity. Well, if you believe in the positivity of the 1D functional, the higher D functional, it is instant. So, and for the computability, it is a direct product of the 1D functional, so it is given by the, we have efficient ways to compute it. But there is some subtlety. I will come back to it later. So it seems that the product functional, it is one of the ideal ways to do the functional, conformal bootstrap functional in the higher dimension. So it is very natural to give a try to see how it works.
Sorry. Don't you?
Yes?
Is it not too positive because it's also positive for non-integer spin?
For non-integer spin.
Yes. Because you're treating rho and tau as continuous parameters. So you can, in principle, just take, look at the rho tau plane, and of course there are lines on the rho tau plane, which correspond to integer spin.
Yeah, this is an interesting question, but for the numerics, we never use non-integer spin, right?
I know.
Yeah,
but
yes.
So you have a class. Well, we check positivity for. Yeah, maybe. I think. I'm not sure. Do you think they're positive? Do we have a good experience? might be true. Yeah. Okay. Thanks.
Okay. So let me pass to the second step, that is the auto approximation after defining the functionals. As the main audience here, they are not from the titles of our Bootstrap meeting. Most of them, they are not currently doing numerics. So I won't be too precise here about the numerical implementation. Here, I just want to, first, it seems auto approximation is a bit controversial terminology. So I must be precise here. It means, here, from me, it means discretization plus refinement. What does this mean? This means that, well, in the early days of numerical Bootstrap, we are using the discretization. Say we have a delta table, and we test the positivity on the different grid. Well, but this is not good enough because our functional, it may look like that. So on the grid, they are always positive, but among the grids, they are not positive. So the refinement here, roughly speaking, it refers to that if you find some negativity here, you just put in one more grid to guarantee that the positivity is saturated everywhere. After some finite amount of iterations, you will reach a, well, close enough solution to the full positivity condition. This is called the auto approximation here. So why do we bother to implement it here for the auto approximation? Well, the reason is instant. The functional action, they are sine squares. They are some genuinely transcendental things. You don't want to approximate a sine square by a polynomial usually. So it is not polynomial. And the second factor is that functional basis, especially the product functional basis, it is especially good for the auto approximation. One of the dilemma of the auto approximation, the discretization, is where to choose the grid. Well, but for the functional, from this explicit construction, you will see that the functional, they are just basically sine square above a twist gap. So above a twist gap, twist larger than twist star, they are like a constant times a sine square. So very few points, they are enough to determine that they are positive above this twist gap. And below this compact twist region, we use a very fine grid. That's the implementation. And the third reason, yeah.
Can you comment? So the functionals themselves, individual functionals, are positive asymptotically, but when you consider their linear combinations do not necessarily have positive coefficients.
Yes. Okay.
Let me finish. So in the case of derivative functionals, this didn't really matter because the leading derivative always dominated. So the important thing was that the coefficient of the leading derivative is positive, and the others ones didn't matter. So here you have a bunch of things individually positive. But is there some other similar dominating property which allows you to conclude that the sum is going to be positive asymptotically?
Yes, actually, you can do some normalization on the functional, and you see that the leading functional, their asymptotic behavior is dominant. The other parts, they are exponentially suppressed, but not so fast. I would like to
dominant, because it's dominant, but it's still so even the leading functional is going to vanish at infinitely many points.
No, you can normalize it so that they look in the precise implementation of our numerics, our functional, it will be something. Well, this is some dragon region, and beyond that, there are some sine squares.
Yeah, sine squared. So it approaches zero at infinitely many points.
No, it approaches a constant.
No, what constant? It approaches zero, right? I mean, it's zero, it's sine squared, so it vanishes at infinitely many points.
Yeah. But I mean, it
So
is
suppose
a
there is some
constant,
other functional which
constant
near
times sine square. The path.
constant times sine
Yes,
squared.
this
Okay.
is asymptotic after the normalization. Yes. The sine square, they have the same double zero in the asymptotic region.
And so what's the claim that this constant is largest for, there is one function which is going to
Yeah,
have this
for the
constant line?
leading functional, let's say alpha 0 or beta 0, this constant is larger than the other ones.
Okay.
They are goes like the GFF, OPE, they are decaying in that spectrum. Yes, so let me point out one important.
But it's, just to come across, so it's larger, but it shouldn't be just constant larger. It should really be, in the case of derivative, this constant was growing with delta, right? And here, this constant, does it grow with delta or not?
Well, let me be more precise.
Yeah.
It is something like C omega minus, sorry, I don't remember, but something like that.
Yeah, but that's not enough to guarantee asymptotic positivity.
Yes, so
Because
you need,
now you have a bunch of constants,
yes,
so
so you need more point. 2 point is not enough. You have the subleading ones. The dominant one is determined, but the subleading ones, you need more point.
okay, so one has to impose this constraint.
Yes,
Okay.
indeed. But
Okay.
you don't need a very dense grid here in the asymptotic region.
Okay.
Yeah, and I want to remark that where does it goes to the non-trivial region, I would say there are some sine square times constant. Well, suppose you are considering some Wn, omega n, and omega can be alpha and beta of both plus type and minus type. If your delta is larger or equal to than 2 delta phi plus 2n plus 3, then there is basically sine square. Below that, it depends on which functional you are considering. So if you put a truncation on the product functional, let's see, if you are considering m plus n smaller than some lambda, you have a truncation on the non-trivial region. That's how it works. Yes, and also the normalization, so that one of the benefits is that we have a uniform or the smooth asymptotic region. Somehow this enhances the numerical stability in our implementation so that we can do it in the double precision. But notably, in the early days of conformal bootstrap, using the discretization, we can also go decently far through this double precision. So the lesson to learn here is that our demand for the arbitrary precision, like 2,000 digit precision, it comes from the polynomial approximation. That is, well, for example, you have a 100-degree polynomial, and your leading coefficient is shift a little bit, and the polynomial, it got changed significantly. This may be the idea. And for the last one is the practical implementation. That is, we implement all the code in the Julia. That is, we write some solver for it, and it is called funboot. Sorry?
I seem to recall that even in the very first numerical Bootstrap papers, before people figured out that conformal blocks could be written as a positive times polynomial form, precision was already an issue. People needed to go to maybe not hundreds of digits, but certainly higher than machine precision.
Yeah, but this issue comes from the bad performance of the mathematical function, I think. At that point, if you choose a better solver, it will be better, I think. Okay.
I don't think it's correct, but we can talk this.
Okay. So in the, we implement all our numerical details here, including some specific pivot rules for this current problem. Okay, so I don't have a lot of time, so let's go to the final session, that is numerical result. The first sign of the completeness is that using different bases of these product functionals, we reproduce the known gap maximization result. For example, the GFF through the L equals 2 spin 2 gap maximization, you got GFF. Yeah. And the second one in 2D and 3D. Yes. The second remark is convergence. Because I can't show the plot or the, so I just show just one data, that is delta phi equals 0.9. Okay, why don't I just draw some pictures first? Yeah. So let's see, 2D CFT, gap maximization, right? What is known is that there is a kink over there. And above that, there is some minimal models. And then further, there is another kink. And our discussion, our numerical exploration shows that there might be some higher kinks, the third kink, and even the fourth kink. So where is here? This is 1/8. This is 1. This is 1, and this is 4. Yes. Here, this correlator corresponds to the 2D critical easing sigma correlator, and this is the epsilon correlator. So the delta phi equals 0.9, where it is somewhere here. Here, if you really committed the derivative basis conformal bootstrap, actually it converges very slow here. So I list some data. So for the derivative, the number of functionals, or we prefer lambda here, that is 1591, 171. Here it corresponds 9, 25, and 35. What is the upper bound? Well, here it is 3.0926, 3.403, 3.35. Okay, then we give some data on the functional bootstrap. I mean, here there is the first region that there is significantly difference between the functional bootstrap and the derivative. Here they are almost coincident, but you look deeply into the third digit or the fourth digit, you can also see their difference, but they are not visible on the plot. They are simply. So why don't we put the fermionic first? For 12 functional, what is its data? 3.3305. 24 data. And for another result from the product functional, that's fermionic plus botonic minus. The data is 3.85. These are the number of functionals. You should compare this line, not the lambda part. Yeah, this is basically the message. So this agrees with the previous study on the 1D numerical bootstrap using the functional, that it seems the product functional or the analytic functional, it has better convergence behavior than the derivative. So here you see the number of derivatives, it almost doubled, but the precision, it doesn't really improve a lot. So the convergence here among this corner, it is very sluggish. And for the fermionic basis, the product basis, you may notice that it is significantly better than fermionic bosonic. There is some reason for that. Why? Because at this corner, this specific corner, the fermionic basis, there is a functional that is called beta 0 minus times alpha 0 plus. This functional, one single functional, it is actually an extremal functional that a single functional fixes the upper bound here. So you can imagine that in the neighborhood of this point, it converges significantly better than the fermionic bosonic type. But it seems they have similar convergence behavior. Also, around the first corner, that is the first kink, the fermionic bosonic, it converges slightly better due to some not yet very clear reason. Yes. So some remarks on the convergence behavior. So our result agree with the 1D exploration that functional, indeed, it is better than the derivative. But why? The first guess is that, well, functionals, it has a double zero asymptotically, so it agrees with the extremal functional we should get. We will expect some double zeros from the light cone bootstrap. Of course, when there is some twist gap. So this is one of the reasons. But this reason, it doesn't clarify why most of the time the FF type, it also works pretty well. I mean, even if you want to reproduce GFF, FF type, although it doesn't have the correct asymptotic spectrum, it also works well. So there is some other reason. That is, if you look at the derivative basis, well, I'm in a schematic here. You will see that for large delta or high twist operators, both of the OPE and the crossing vector, they are exponentially decaying. This is not true for the functionals. Because the functional, if you don't normalize it, this decays exponentially, but this grows exponentially. The exponential factor, they cancels. So this is a power law convergence in terms of the OPE expansion. So the high twist operator or high delta operator, they are less suppressed in the crossing equation than the derivative basis. This is another reason that why the functional will work better than the derivative. This also hints us that if we can cook up some other functionals that has the same property that it has a power law convergence, we may also expect that it converges better than the derivative.
I actually don't understand this comment because, yeah, these statements about power law versus exponential, they all depend on how you normalize OPE coefficients. So in the natural normalization of OPE coefficients adapted to the radial coordinate rho, I think also the first equation converges in the power law with the power law speed.
Sorry, could you repeat?
I'm saying in the natural normalization of OPE coefficients adapted to the rho coordinate, they are not exponentially suppressed, they are only power law suppressed.
Yes, but by that normalization, your conformal block also changed, right? The normalization of the conformal block.
Yeah, but since this is arbitrary, this cannot affect the performance of the numerical algorithm.
Okay, I'm not sure about that. Let's discuss about it later. Yeah.
Okay, my question, I don't have a question anymore, but I think I can comment on what you said. I mean, this is OP coefficient times block evaluated at z equals a half. So you can ask how fast this converges, right? And that's a fair, like with delta. I think both are, so the first should be exponential, I guess, because the convergence of the conformal block decomposition is exponential. And now you're saying the second is power law.
But if you just change derivatives to row variables, does it change? Just change the derivative to row variables. I think that was what Dali-Millet observed, right?
That was about the basis of the functional components, and they may look nice in those but of course, the row derivatives with respect to rho and rho bar are linear combinations of derivatives with respect to z and z bar. Very good. Okay.
Okay. Okay, at last we go to the third kink that we observed, and maybe there is a fourth kink. We got some hint from it, but it seems that 144 functionals that kink is not sharp enough. We are trying to push it even higher. This kink, what is its nature? Because the gap scalar channel gap maximization till now, without additional assumption, I think in 2D and 3D, in 2D they both correspond to Ising model. And in 3D, they also correspond to Ising model. So it's tempting to guess that this is some interesting theory. But our numerical exploration suggests that this must be a non-local theory. Non-local here means that the stress tensor, it doesn't have a stress tensor. The leading L equals 2 channel, it is something like 0.29. You may think this is a numerical artifact that if you push very high number of functionals, then it will go to 2, but actually it seems not. If you push it up, then this will go slightly up. And there is some other reason that if this is a stress tensor, then we must have this Virasoro structure in our spectrum that there is a step of 2, the dimension of the primary field, but we didn't observe that. So it must be some long-range theory, and because this is very high, so we guess it is some very non-perturbative, which means that maybe it is out of our exploration of epsilon expansion, something like that. Yes. And let me comment on the result of the 3D CFT. That is, well, we reproduce the kink. We use the 18 functionals here already. This is the 3D kink, and also the GFF, the familiar spectrum. Sorry, let me draw the solid line. Yeah, why in 3D we didn't go far? Because that power law convergence, the ways we use to evaluate the functional, it seems there is some subtlety. That is, let's say, omega of f delta L. When the omega is large, well, in that expansion, when n much larger than 1, delta also much larger than 1, and n much larger than delta. So it is dominated by 5.5 plus. It goes like this. So for small delta, this expansion, it works pretty well. But for large delta, it converges very slow. So what does this mean? This means that if we want to consider high spin, what does it mean by high? Let's say spin 20. Then this is much harder than the spin the delta 0.5, because spin 20, it must start with delta equals 21. So this is the reason why we didn't go very far in 3D. A possible solution to this situation, that is the computability of the product functional, lies in that there is very strong indication for the product functional. You also have the rational expansion. That is, I don't mean that you want to expand the sine square factor in terms of some rational factors, but I mean the sine square times some rational factors. How to say that? Well, the first reason is from the numerical exploration. If you analytically continue, you will see below the unitarity bound, there is a lot of pole structure over there. And there is rigorous mathematical result that generalized hypergeometric function, it can do the rational expansion. So for 1D, we can do the rational expansion. So for 2D and for 3D, I guess we can do it. We just don't know this kind of rational expansion. Okay, so at last, I would like to say some future direction. As you have seen, all our exploration is limited to the single correlator right now. But luckily, I think tomorrow there will be a new paper on arXiv by Miguel, Upper team, and Kosik, also my colleague. They did the 1D functional for mixed correlator. So 1D functional for this kind of correlator. I'm not so sure about that result, but I think if with that functional, we can easily cook up some higher dimensional product functional for mixed correlator. And we need some outer approximation for the mixed correlator situation. I don't know how it will work. And the second one is about the double precision.
But is this semi-definite constraints or still linear programming constraints? I don't know how
mixed
to say
operator, you can write several crossing equations, so you can construct some semi-definite programming.
I know you can, but if you do ON symmetry or so, you don't always need semi-definite programming. You can do, if you write that, then it might just be
no.
linear
Here,
programming problem.
here I don't want to say ON symmetry. I want to say different operator.
Okay.
Sorry.
Thanks.
Sorry for this misleading. Yeah, they are of different dimensions in the external dimension. For the ON functional, it is already has been constructed. Okay. So for finally, we want to say something about the precision. Yeah, it is clear that the double precision, we cannot go infinitely far. Beyond that, we need to use, instead of arbitrary precision, I propose to use extended precision. That is double precision or quadruple double precision. It is essentially different from the arbitrary precision. Well, arbitrary precision, you can think of it as some big integers, actually. But extended precision, you are using several double precision floating point to approximate one high precision floating point number. What's the benefit? Well, the benefit is GPU acceleration. That is, if you want to do if you want to implement CUDA in the arbitrary precision situation, I guess you will spend all the time copying the memory between the CPU and the GPU. But for the extended precision, that is, for example, double precision, that is 32 digit, you have, or even higher, you have the well-established library. That's called a Campari. That is, someone has already implemented higher extended precision in SDPA to explore that this package, this library, it works well for higher precision. So this concludes my discussion of our study.
Very nice. Yeah, just so I understand. So this first part of the plot, it's with 16 digits that you can reproduce this plot?
Yes. These are all machine precision. The solver itself is, you can choose your precision. But all our study is in machine precision. The tricky part is we use some interpolation from Julia, some external package. But it seems that package, it is super slow compared to the Mathematica implementation of interpolation. We don't understand it why. Maybe in the future we will write ourselves a B-spline interpolation. Yeah, actually most of the time they are wasting among the interpolation.
So, man, it's been a long time ago, so I guess not everyone remembers what was done in these early papers. I just want to remember that in 2008 paper, Of course, double precision was used with discretization and the grid. In 2009, when we first produced the 2D king with Alessandro Vicky, it was, of course, also using double precision. In the first 3D easing paper in 2012, where the king was discovered, it was done using double precision, no big deal. In 2014 paper, within the C minimization paper, it was the first paper where multiple precision was used. And here I would like to comment about possible needs of multiple precision. So I agree with Zechan, your comment that one reason for using a lot of precision comes from the polynomial approximation and the fact that those polynomials have high degree and there is a lot of cancellation when you evaluate those polynomials. But that's not the only reason. In fact, it's a well-known fact in optimization literature that when you have problems with continuous sets of constraints like what we have here, you are forced sooner or later to go to multiple precision arithmetic simply because you have accumulation of constraints very close by. And so I don't know if what you're using in the current algorithm. Are you using linear programming right now?
Yes, but with some of our self-written pivot rules to guarantee.
Okay. So using the linear programming. So now, as you know very well, in the simplex method, at some point you have to invert a matrix.
Yes.
Which comes from a bunch of constraints. And so if those constraints are very close to each other, and that's what you're going to have when you use your refinement, that matrix is going to be nearly degenerate.
Yes.
And you have to invert that matrix, and sooner or later you have to go to multiple precision. So that was the reason why in 2014 we had to use multiple precision. So I don't think there's going to be I don't think like reduction to double precision should be a goal in itself. Okay, it would be nice to reduce the number of digits we use by a little bit, but sooner or later, it's just unavoidable. We have continuous sets of constraints, so multiple precision is going to be needed at some point. You can delay it, but you cannot fully eliminate it. It's just unavoidable.
Is it possible to use some dynamical precision that is, initially you use some...
You can use various tricks, but you should not hope that by finding some miraculous algorithm, you are going to eliminate the need of multiple precision forever. It's just unavoidable. It's a well-known fact of optimization problems with continuous sets of constraints.
Yes.
Okay. Otherwise, very nice work.
Thanks.
Any other questions?
So in this outer approximation, as you probably know, Walter also implemented some version of it, and he saw that, right? You say you have a bunch of points, you check positivity, the functional is negative in between, so you add a point, and then you iterate this process until your functional is positive everywhere. But he's observed experimentally, and I don't know how or why exactly, but experimentally he saw that you really needed a lot of points near zero of the functional, because otherwise the functional would always find like a little bit of a small window where it would dip and become negative. Do you see the same thing, or do you just...
Well, the precise implementation is a bit long story. So we use some double phase auto approximation. So you have the big grid. Where is the big grid? Okay, let's see. You have a very fine grid here. Not very fine, sorry. And you find some negative region. So our precise implementation is that we will add some point here, 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 here for each saturated point. Then we go to a small grid, that is, erase all this positive grid. Then we run the precision. And then we come back to the big grid to check its positivity. So it's using this kind of techniques. And the precise, I can send you the draft, and there is described. It converts pretty well, maybe due to the this is linear programming instead of SDP. But SDP, I think you can use a similar construction. You just check where the positivity is saturated.
So you found that the convergence improved a lot near some specific point, but might not be, well, okay, let me, can you discuss also, for example, the decos 3, because you didn't have time, I guess, to talk about convergence there near the icing model?
Yes, actually, among all these kinks, the convergence is significantly improved, whatever basis you use. For example, derivative basis or some others. We are not very sure about the precise reason. Yeah, but versus. Really? Okay, then in 2D, I'm pretty sure in both bases, at the kink, it converged better. In 3D, I didn't do a very close investigation recently, so I don't remember it. Yeah, maybe that's true. Here, the 18, they are like in the third digit or the fourth digit, they are convergence. So if you draw it on the plot, you cannot see the distinguish between the plot and the precise easing point. So they are like precise at the kink. So this is the convergence of the functional. Well, the spectrum uses there is all in 18 functionals. So you don't see a lot of operators in the spectrum. And in 2D, yeah, in 2D it is very precise, even for the higher twist operators. Here we have the precise result, right, in the easing kink. And you can compare their, well, for example, here I remember like 50 functionals or 40 functionals. Yeah, maybe 40 functionals. For the leading coefficient, that is 1. You get something like 8 digit or something like that. But for the very sub-leading ones, you get still 5 digit. And also for the OPE, they are very precise, at least here. Yes.
So, like, we know that the actual integers at high end aren't part of the real spectrum. So at some point, I would expect that to become important, or I don't know, the error from that to seep into your. You should use the mic. So at some point, I expect the error that comes from assuming exact zeros at integers to leak back into your low-lying operators. Do you see that at all, or is that not correct, the way I'm thinking about it?
Sorry, could you repeat?
So the functionals you're using have sine squares, which have
Yes.
exact zeros
Yes.
at integers.
Yes.
But we know that real theories don't have, they only have that asymptotic.
Okay, I understand what you mean.
Okay.
Yeah, this depends on the initial construction of the grid. So you intentionally avoid such, well, there is no issue of it, I would say. The all-in issue of numerical stability, it comes from, as Slava said, the yield condition of the matrix for that is called the basic feasible solution in the simplex algorithm. This is all the numerical instability comes from. And our pivot rules is implemented to get rid of this, to avoid this yield conditioning, actually. So for the precise zero, it never really comes in, I would say.
Okay, let me. So I remember at some point David wrote some paper where they took the derivative basis to some high derivative, and they were able to see the fit to the 1/L expansion of the Lightcomb bootstrap coming out of the numerics. But for you will not be able to see this at all, right? So at some point, your results will have to differ from the derivative answer. Because, I mean, you're not going to have a 1/L expansion. Your zeros are exactly at integers, if I understood correctly.
it has exactly 0 above this this gap, this twistor gap, and below that, you don't necessarily have exact zeros. I must say that, for example, for the alpha type functionals, well, it is already erased. Alpha type functionals, alpha n, delta m, it is not actually 0, but delta nm. So it is not. Below some twistor gap, you don't have these zeros, the guaranteed zeros. Some functionals, they are responsible for these operators, I would say. They are like, well, the twistor gap is very high, so yeah, there is very few operators over there. They are just, well, if they are a pure operator, they are just appearing to guarantee the positivity asymptotically, I would say. They are not physical.
Please repeat the question.
Yes, I hear the question clear. That is,
No, please repeat, yeah.
yeah,
Okay.
he is asking how to choose the functionals in the product basis, right? Yeah, well, we are using a very stupid ways of choosing the functional. Suppose we are using the Wn minus Wm plus, right? And here W could be alpha or beta. We just demand that n plus m smaller than some lambda. This is our criteria. So you will notice that, well, for the fermionic FB category, we have less functional. That is due to that in the fermionic basis, beta 0 is always 0. So it is excluded. So we have less. Otherwise, they are the same. So the choice is very naive. We didn't even try some more interesting choice. For example, that is, for example, this is some triangles, right? Triangles in the M and N. So you can choose some different choices, definitely. Yeah, there is another interesting comment. That is, you can try the mixed of FF and FB. It works, and it works as well as a single basis, I would say. So we didn't do a lot of exploration in this direction. So this is a clear sign that you can choose some different bases, or even the basis from the dispersive sum rules, they cook up some positive functionals. You can put it in and do some mix. This is also possible. And even you can mix with derivative, I think.
Can you also comment? So you comment on the number of functionals when you compare the different methods, but how about the time of the implementation? Because I guess your functionals are a bit harder to evaluate.
Indeed, they are. If you say the evaluation of this 7F6, indeed is harder. But this is something like once in your life, because you are doing you evaluating based on the 1D functional, right? Well, 1D functional, you can create a very dense grid up to, let's say, delta phi smaller than 2.5, and calculate a lot of delta phi, and for each delta phi, you calculate the delta up to very high, let's say 800, for example. This is what we did. And after you did it, you can use some B-spline interpolation to explore the intermediate point. It works better than you might initially thought. B-spline, if you use a very high order B-spline interpolation, you can get, let's say, more than 80-digit precision or something like that. So it is reliable. As long as you've done it, you get, let's say, 400 gigabytes of data containing all of it. You don't need to do it again.
Very nice. So let's thank Zeshwan. But before you leave, I have